All right. Today, we're jumping into a really cool idea that nature actually figured out first: particle swarm optimization, or PSO for short. It's this incredible algorithm that shows how a group of simple individuals, just working together, can come up with some truly brilliant results. Okay, so just look at this for a second. What you're seeing is a swarm of individual points, and they're all moving around without any kind of leader. No one's calling the shots. And yet, look at them. They're all closing in on a single target. So the big question is, how on earth do they do that? How do they coordinate to find the best possible answer when nobody's in charge? Well, the secret isn't some super complex master plan. The whole algorithm is actually inspired by something you've probably seen 1,000 times: how birds flock together or how bees swarm. It really all comes down to this: simple, local interactions can somehow create this massive, intelligent, coordinated action. It's pretty amazing. So what exactly is the mission here? What's the problem this swarm is trying to solve? Well, let's just imagine they're all on a search for the single best spot in this huge unknown territory. Okay, so this colorful grid you're looking at, think of it like a landscape of possibilities. The blue areas, they're not bad. But the red and yellow spots, now that's where you want to be. The swarm's entire goal, its whole mission, is to explore this entire space and find that one single highest peak. In the biz, we call that the global optimum. Right, so how does a group of completely independent particles pull this off without a map or a leader telling them what to do? The answer, and this is the cool part, lies in just a couple of incredibly simple rules that every single one of them follows. And I mean it. Believe it or not, all that complex, coordinated searching we just saw, it all boils down to just two fundamental ideas. That's it. Two ideas guiding every single member of the swarm. And this breaks it down perfectly. You've basically got two competing forces at play. On one side, you have what we call the cognitive component, which is just a fancy way of saying trust your own experience. And on the other side, you've got the social component, which means learn from what's working for the group. So let's dive into that first rule. This is the P-best, which stands for personal best. Basically, every particle has a memory. It remembers the absolute best spot it has personally found so far. You can think of it as a little pull, an anchor, towards its own past success. It's all about self-trust. But it's not just about what the individual remembers. This is where the big best, or global best, comes in. At every single step, each particle also knows the single best position found by anyone in the entire swarm. This is that social influence we talked about, that magnetic pull towards the group's biggest win so far. So every single particle is doing this constant balancing act. Its next move is this blend. A little bit of its own momentum, a little pull towards its personal best spot, and another pull towards the group's best spot. It's like a nonstop tug of war between what I know and what we all know. And that balance is absolutely crucial. Think about it. If everyone just blindly followed the group's best discovery, the whole swarm could get stuck on a good spot, sure, but they might miss the perfect one. That personal pull, that little bit of stubbornness, is what keeps the swarm exploring and stops it from giving up too early. Now, this is a really elegant idea, right? But here's the thing. It's not just some cool animation or thought experiment. This super simple algorithm has some seriously powerful uses out in the real world. And honestly, the range of things people use this for is kind of staggering. I mean, PSO is used in really complex engineering. We're talking about designing things like antennas, aircraft wings, even amplifiers and circuits. And it doesn't stop there. It's also used to tackle these ridiculously hard scheduling puzzles, like figuring out the absolute most efficient way for a business to operate or assign tasks. All right, so this whole system works beautifully for exploring and finding good spots. But it does bring up a pretty important question, right? If the swarm is just always searching, how does it ever know when to stop? How does it decide, okay, we found it, job's done? Well, there are a few pretty common sense ways to end the search. For one, you can just set a hard limit, like a maximum number of attempts or a time limit. Or you can tell it to stop once it finds a solution that's good enough for your needs. A slightly smarter way is to have it stop when the best solution just hasn't gotten any better for a bunch of rounds in a row. And finally, the most obvious one, it can stop when pretty much all the particles have landed on the exact same spot. Okay, so let's zoom out and look at the big picture here. What is it that makes this algorithm so powerful and so popular? The real genius of particle swarm optimization is just how simple it is. It's the perfect example of what we call emergent behavior.
You don't have to code some grand, complicated strategy. You just give each little particle a couple of simple rules. Trust your own experience, but also pay attention to the group's success. And from that, this incredibly effective global intelligence just emerges. It's fantastic. And because it's built on these super intuitive ideas, it's also remarkably efficient. The algorithm just keeps updating each particle's position based on that simple balance of personal and social knowledge. And by doing that, the group as a whole is constantly creating and testing new, better solutions.
And that really leaves us with a final, pretty big thought. If a strategy this simple can solve such complex engineering and planning challenges, what other massive problems out there, in science, in business, maybe even in our society, are just waiting for us to solve them by simply trusting the collective wisdom of the swarm?